There's seats there.
Getting close, the moment is approaching. It's not here yet. We're just going to let a few more people figure their way in, and then we'll get started and go through it. Thanks for bearing with us. First session is always a bit chaotic. Major downfall. If you are running extremely low,
Sorry.
Monday, week 6. So much stuff.
Hi, is anyone sitting there right now? Anyone sitting there? Is there a space next to you? Is there a space there?
Full more.
We're having one like this Friday.
Which one, okay? We can. Okay, can I go bring that there? Goes through
my muscle every stretch and I can rotate and I wake up for a the guy on the festival is not even started his life. What the point of
I really want to get to I really want to get to that will help quite a bit.
drop your...
Doing this is going to be one, and it's so much good content.
That's about it. How's the audio? All right. Just quiet. Alright, I guess that means it's time to get started. Let's go. So welcome everybody, thank you so much for being here. It's great to see the room packed out like this. I'm sorry we don't have more chairs for anybody else who has one of those seats. But thanks for being here. I'm really excited to get started. We've got a lot to go through. The first session is always a bit chaotic, but hopefully things will settle down as we go forward, and this will be really rewarding for everybody involved. So bear with me a second, and I will pull up what we're going to go through today. Cool, we good to go. Any issues? Everything good? Nice, there's an issue, Raymond? We have, don't worry about the slides, they barely cover anything. That's not what we want to do yet. Don't worry about the lecture slides, they barely cover anything. We'll be done with this in 15 minutes, and then everything else is accessible through email. If you don't have the emails, it's accessible through Discord. Again, I'll go through all of that as we progress, but thank you for asking. Any more issues? Can you hear me? Can you hear me? Good. What about you? All right, nice, very good. Yeah, let's begin then. Let's begin. Question?
I think maybe it's me, or maybe there's an issue with Discord because it says message one of the moderators to have access to the channels, but it's like you can't message the moderators because you're not in the channels or group with them.
This is the Discord pod. You can help with that.
Yes. But yeah, please feel free to go ahead. So
Yeah,
I try to message.
All right. So yeah, let's get into it then. So welcome everybody to the ChatGPT lectures. The whole point of this is to get to where we can understand what ChatGPT is, how it works, why it's a breakthrough, and apply some of that in whatever you guys are working on. So I'm really excited to get to that point. It's going to start off simple, so don't be scared if you aren't familiar with any of the complicated stuff that you might have heard of that underpins this. And we'll build it up as we go over. So we've got 11 sessions over 3 weeks, and it's going to be an exciting journey. Who am I? I'm Harry Berg, your futuristic lecturer for the series, and I'm here with thanks to Andrei Kravchenko. Andrei, do you want to say a few words now? Okay, cool. So Andrei's been very kind and helpful in coordinating all of this. Really, I get to reap the benefits of it and stand up here and get to teach you guys, which is the most exciting thing for me. But Andrei's put in a lot of work to get all this together, get everybody from the department on board, and help distribute that to wherever you guys found out about it. So, so thank you. Ahmed, you wanted to say a few words, right? This is Ahmed, the community leader.
Hi everyone, hello. Thank you for the introduction. I'm Ahmed and I'm the community leader at Aicore, one of many. First of all, just super excited to have this many people with us today. And mostly what I do is just manage the community and make sure that everyone is happy in Aicore and is having a great experience as the one I had. As Harry was mentioning, we have the Discord server up and running, so if you haven't joined yet, make sure you do through the email that was sent out. And message me or Charlie, a community member with us here as well, and we'll grant you access as an Oxford attendee. We have several channels on Discord, and I really want you guys to engage with them, just so we can gauge what kind of help you need going through the lectures, or if you have any issues, or if you're really happy, or if you're really not happy. Just share your thoughts with us so we can improve going forward. You have the forum as well, so the forum, just post any discussion you want about anything we're learning here, or anything at all that is deep learning related. And yeah, that's everything from me. Join Discord, and I'm on my email, so I'll grant everyone access. If you can't message me, send me a friend request, and we'll take it from there. Thank you.
Thank you very much. So yeah, basically Discord is going to be the main place to access community support and announcements. So if there's anything that changes unexpectedly that we need to make you guys aware of, we'll share it through Discord. And if there are questions that you guys have which either you don't want to ask in lecture, or you're online watching this, then Discord's the place to post those. So there's a forum channel where we'll see all of the questions and challenges that you guys are facing, and we'll be able to address those. And anybody else who has similar issues can look back and find responses to the same issue if they have that. Any questions or issues about Discord? Everybody on Discord?
Yeah, getting like 15 friend requests.
Right, cool. Alright, Charlie, give us a wave. Charlie, give us a wave. Does Charlie also help with the community stuff? His face didn't make it to the slides, sadly. But yeah, Discord is the main place. I can't emphasize enough. Like, Discord is the place for any updates which are going to go out from now. I don't want to have to email any more people, please. And there's a good log of all of the historic issues that people are facing with the stuff that we're going to go through together. We're all going to be going through all the same content. You guys are likely going to face issues which are exactly the same as what other people are facing, and so that's the place to check it out. On a related note, you guys are lucky enough to be here in person. I hope you're excited and to have the opportunity. And at any point as we go through things, whatever is unclear, you can shout out. I just want to make that really clear. Try and do it at an appropriate enough moment, but feel free to stop me. Harry, hey, I've got this question, I've got this issue, what's going on, as we go through. The main time you probably need to do that is when we're going through any of the theoretical stuff, or I'm demonstrating something. What did he do there? What does that mean exactly? Feel free to ask. And between the theory and demonstration, we'll have a good amount of time for you guys to stop and get into the hands-on programming yourself. Like, I really want as much of this as possible to be you guys spending time, fingers on keyboards, actually implementing this stuff, so that by the time you finish this, you understand how it works inside and out, how to honestly debug it, which is the real skill which I want you to develop, and then you can pull apart the examples that we've used and make sure they fit into your own work. So I'm sure you guys have a lot of interesting stuff which you're working on, which you want to apply this to. Great. Any questions or issues so far?
We have a Discord access.
It just says my link's invalid.
Your link's invalid. Ahmad, you can help with that, right?
Yes.
There's a gentleman just there at the back in the white shirt. Cool. Great. So outline of what's planned. We have this big series. It's been called the ChatGPT lectures, and it breaks down into these three parts. So these are the three things that we want to go over. They each have kind of a quite contained focus. So it might be the case that you only want to understand how to program for deep learning. You're not interested in later stuff, or maybe you're already very comfortable with that. You want to get involved with the later stuff only. Feel free to switch it up like that. The full schedule is available. You can see what's there. These are the dates things are happening. They'll be here in this room, and yeah, basically that's what we're going to go through. Each of those has a few lectures, and all the material we'll get into in a second. Give me a second. There's a lot of talking up there. I always forget how hot this is. All right, cool. The next really important thing is to access all the material through the Aicore portal. If you're in any of the emails, you will have received the details of how to access this. There's a form, you sign up, you get an email, etc. And then you can log in. And that is the main place where you can access all the notebooks and all of the practicals that we're going to work on. And in the future, all of the videos as well. This is being recorded there and here, and so everything should really work out as long as you have access to the material on the Aicore portal. If you don't, again, I can help with that. So I'm going to bring up slides like this a lot, just to highlight like where we are in the journey. So welcome. This is the overall series from Neural Networks to ChatGPT, and the first part is a focus on programming for deep learning. That's what we're doing. That's what we're starting today. So part 1 starts today. Part 1, the first part of it, is an overview of the essential ML concepts. And this is what I want to get into now. Fantastic. Cool. So take a moment, everybody, just to make sure you got all those things set up. Make sure you can access Discord. Make sure you access the Aicore portal. And cool, great stuff. And then we'll get into it. All right. So just whilst we're doing that, a few questions. Raise your hands. Like, who understands what machine learning is? Roughly. Cool. Good. Most of the room. Yeah. Nice. Who has built their own? Who's built anything? Some kind of their own application using machine learning, even if it's just a toy example. You built something with it in PyTorch. Okay. A few people. Maybe half. All right. That's nice. And who's used PyTorch? Good, that's a large number of you, wasn't expecting that many. Great stuff, that should make it easy then. Awesome. Cool. So this is what your Aicore portal should look like. This is where you can access the, that's not what I want, I want the opposite of that. This is where you can access all the material. So as we go through it, we'll release more pathways, which you can access down here. And they'll basically be step-by-step guides of the lessons containing the notebooks and the practicals that we're going to do. And that's it. So this is the main place to access this. That's what we're going to jump into now. Everybody ready to get started? That's the end of my intro. There's no more slides. I hope you understand you don't need the slides. They weren't really that important. This is where the content begins. Okay? Awesome. Can everybody see this? Can anybody not see this? Is always a better question. Raise your hand if you can't see this clearly. It's a little small. Very shy. So I'll zoom in a little bit. And the brightness okay? Again, I'll stop asking, but just want you guys to know, if anything isn't okay at any point, feel free to stop me, ask questions, get involved. I'd rather not be talking at you, and I'd rather be this two-way. Isn't that right? Yes, exactly. Cool. So the first pathway you want to go through is this one, right? It's called programming for deep learning. It's going to cover the fundamentals of coding up deep learning, specifically neural networks, and we're going to use PyTorch to do that. So there's 11 lessons in here. We probably won't go through all of them like holding hands in these lectures, and instead we'll kind of focus in on the important ones. I'll let you guys check out some of the ancillary ones in your own time, and when and you can do that whenever you want. You'll have access to this as we go throughout the program. So the first one is this essential ML concept, and that's what I want to go over today. The whole point is just really make sure everybody's on a level playing field. We all understand the jargon and the terminology that you're going to hear constantly as we go through this. So if you hit continue up on the top, then you can see the outline of this pathway. And the first part, as you see, essential ML concepts, notebook. You can hit this button to open up the notebook. This takes you to Google Colab. Google Colab is actually an incredible tool which allows me to get you guys in the room without having to do any Python setup, which is always the nightmare part of things. So this is a notebook which contains both obviously text and diagrams, but also contains blocks of code. There are actually none in this notebook, but there are blocks of code where you can write Python, the programming language that we're using, and run it without having to worry about any of the dependencies on your computer. Everything will work fine. Raise a hand who's used Colab before. Fantastic, that's awesome. Raise a hand who hasn't but has used Jupyter Notebook. Even that's fine. Like, it's exactly the same thing. This is INV file. It's an interactive Python notebook file. So I'll take a deep breath. I feel like I'm rushing it. My watch is out of battery, but I'll try and keep track of the time. I'm only 30 minutes in. This is going good. So what is machine learning? That's really the first thing that I want to cover. And I think the way to start introducing that is by looking at this illustration, right? Almost any problem can be framed as having some input and some output, and you want to know how to get from that input to the output. Let's say you've got an autonomous vehicle, it's meant to be autonomous, it's driving around, it's got camera inputs. The outputs you need are which direction should I turn, how much should I accelerate? Let's say you've got a bunch of images, those are your inputs. You need to get to an output, which is a classification of what's in the image, or something like that. Any kind of problem, maybe one that's particularly relevant to the title of the series, including if I've got this input text, what's the text that comes next? That can be framed in the same way, this input-output relationship, right? And between those pairs of inputs and outputs, at any given point, there's some function. Some function performs that mapping between them. And the question really is, like, what's that function, right? Firstly, some examples. You know, any problem can be framed in this way. So, you know, some simple functions which you know what they are things like, well, let's say if I've got an email, that's my input, I need to know, is that a valid email? We know what that function is. Like that's a very easy one to write down the rules for. You can simply say, you know, does it contain that symbol, maybe something a little bit more complex, but you can write down the rules for it. That's a simple function. Force equals mass times acceleration. Another function which we've figured out, you know, not such a simple one, but we figured out that, and we know the relationship between those two inputs and outputs. Those ones are easy, relatively. Some functions, like these ones, are really not easy to understand how to write down the rules for. So let's say your input is the previous movies you've watched. The output you want is which movie should I recommend? Knowing how to take those input movies watched and turn those into which movies I should recommend, that's very hard to do. Very hard to write down the rules for. You think about it, right? You know, how would you define that function? It's like, okay, if they watch this genre, then recommend it again? Not really. It's more complicated than that. So there are a lot of functions which aren't so easy to write down the rules for. Another one down here, again, relevant to ChatGPT, which we're going to be talking about, is, okay, I've got a text command. What should be a useful response from an AI chatbot system? How do you write down the rules for that? That's really tough. That's really tough. But how many days have we got? I think 16 days. You will know the answer. Okay? Again, guys, any questions? I really want to open the floor up. So any questions, you can jump in at any point and we can go through it. Otherwise, we might actually finish early and have time for a drink after. So machine learning, right, back to my question of what is machine learning? Machine learning is having the machine figure out what this function is for itself. Because these things, like I said, it's hard to write down the rules for. So the question is, can we just get a computer to do it? Can we get it to figure it out for itself? That's, we're going to be doing a lot of that in these lectures. We'll talk about some of the components behind that today, and we'll go through like the exact steps of implementation over the next few days. But yeah, what is that function that takes that input we have and produces the output that we want? Cool. Everybody happy? Anybody unhappy? Good. Okay, a few examples of some input-output functions. Anybody got any ideas you want to bring to the table? I gave the self-driving vehicle one, and what else did I give? The movie recommendation.
What, like just any?
Yeah, just to give some more examples around the room.
When your computer changes the brightness of your screen based on how light it is in the room.
That's a great one. Yeah, exactly. So inputs, things like, okay, what time is it? What are they doing on the computer? Output, like what's the percentage brightness? Brilliant, exactly. Great example. Any others? Typical machine learning use cases? Anybody?
Extending regression.
Question.
Sorry.
You go.
Extending regression, for instance, beyond like what it has been fed into the algorithm. So
can you explain what are the inputs there? What are the outputs?
Well, so the output is forecasting y based on x.
Mm-hmm. Yeah, so that's a very general answer. That's exactly what we're going to do next. Yes, that's the general formulation. we have for the regression case, which is where we're predicting a continuous output. So you have some inputs, some input values, whatever they are. They could be, you know, the time they spent on the laptop, the time of day it is, and the output is that continuous value. What's the percentage price? Cool. Another example?
Object detection.
Object detection, exactly. Again, yeah, you've got images or video, that's your input. Your output you want is, okay, what's the bounding box around the object in the image? Great, I think we're getting somewhere. Cool, that's easy for you guys. So let's move on, and now basically look at this nice GIF, essentially. And all this is showing really is that this thing on the left-hand side is one of those functions. It's got an input down here, and it's got an output prediction over there. And so for any different value input, it predicts a different value. And you can see that line changes. It changes so that the function changes. The input-output relationship changes between when the parameters of this function set. So you can see on this right-hand side here, I've got two axes. This one says weight, this one says bias. The bias is like the y-intercept. We'll get onto these details later, it doesn't matter. But basically this parameter moves it up and down. This one changes the angle. The point here, nothing more complicated than this, is that different functions can be controlled by different parameters. So if you change the parameter, the input-output function changes. And there are many different functions which you can have, right? You could have a straight line equation, you could have like a sine graph, or whatever mathematical function you can think of. A lot of them can contain parameters. And as these parameters change, the way that the input is turned into the output changes, just as you can see here, okay? Inputs come in, predictions come out, and that's because these parameters are changing. All right. So a big part of what we'll do over, especially this week, is basically figure out how do you change the parameters of different models so they represent different shapes, okay? For more and more complicated examples, this one's very simple. Got one input, one output, and you can change those parameters to change the function. I think that this is a really useful framework to think about machine learning algorithms, is that they consist of these four components. I'll walk through each of them step by step in a second. The first is the data. The second is the model. Third, the criterion. Fourth, the optimizer. So basically, any machine learning algorithm which you have is going to most likely contain these four components in different ways, in some different permutation. You know, you could have everything the same, but the model's different. Everything's the same, but the data's different. And that will really define your machine learning algorithm. So, what are those things? The data is the set of examples that appears in your data set. So the data set it usually consists of two things, right? We've got the features. These are the inputs to the algorithm, and then they're the thing we're trying to use to predict what the output should be. And then we've got the labels. The labels are the outputs. So the features are the inputs, the labels are the outputs. You might also call the labels the targets, or just the outputs simply. But if you have, a lot of data sets have this formulation where they have, a set of input features, a set of output labels, and those are the things you're trying to map between. So again, the image classification or detection example, you have these input features, which are your images, and the output targets, which are the locations of the object in the image. Cool. So, example data sets here, you might have a large body of text where the examples are different sentences. A set of examples containing images and their classification. So the images there would be the features, classification would be the label. And a set of examples containing features of different houses and the price of that house. That's like the canonical exactly, yeah. That's machine learning 101 example, right? The house pricing problem. You've got features of the house, and you've got a label, which is how much is the house worth, and you're trying to learn how to map those two things together, so that in the future, without having a label, you can look at a new house and predict how much it's worth, right? And that's the goal here. The goal here with all of this is to be able to use data to learn the function, and then use the function to figure out what's the label when I don't have it. So how can I use the function to get the correct label predicted for examples, for unseen examples, for examples in the wild? So if I've got my self-driving car, again, I gather a big data set, there's lots of images and videos and what the driver did in that situation. The whole point of that is that I want to be able to use it when there is no driver, right? So you don't have a label in that situation. That's the whole goal of what we're going through. But, zoom back into the data. Talking about the data now. That's big enough, right? Of course it's not big enough. Come on guys, please say something if it's too small. Like, that's tiny. So, it seems to not get much bigger, but anyway, it's all on your portal, so check that out if you can't see it. So I want to show this example here, where I've got like the more mathematical formulation of them. So over here I've got some features. You can see that this is a vector. It's a vector, that means it's a single example here, x, I. Might have a data set, lots of different examples in it, lots of different houses. Each of them have these n different features. So the example down here, where I've actually got the numbers in, this is an example where you can see, okay, this represents a single house. The first feature represents the number of rooms. The second feature represents the age of the house. The third feature represents the age of the last owner. And so that's the way that these examples might be represented mathematically. But a lot of the time it's a vector of features, just a list of numbers. And in this case, I've just got a scalar label. It's just a number. And so that's kind of how the house pricing data set is formulated between a set of lots of different vectors of examples, and each of them have this scalar label. Simple stuff, right? Not a heads, it's simple. Good stuff. We'll get hands-on in just a second. I'm just going to show you up to this point. So that was a single example that I showed you previously, but you can also put all of the examples in a single matrix. This is important to understand because this is a lot of the time, like when you print numbers in your programs, this is what you see. You see the big feature matrix. And so what this is here's all the different examples in the different rows, and here's each of the different features in the different columns. So I've got what have I got? I've got an n by n matrix. That means I've got m examples. Each of them has n different features. So I'm going to have 100,000 different houses, be my m, and 3 different features. So I have 100,000 by 3 matrix, that's my feature matrix or my design matrix, and that's what the inputs look like. This is the formulation of the data when it comes into my machine learning system. My goal is to be able to predict what should the output be for each of those examples. And so I might have an example, I might have some value like this, x34. What that represents is the 4th feature of example 3. Okay? Those are what those indexes mean, and we'll see a lot of those feature matrices. All right, cool. We'll get to this stuff. Okay, great. So that's the first thing that we're going to cover. Now, I want us to get hands-on with it. So there's a lot covered there, all about the data. I hope it's relatively familiar to you guys or relatively easy. If it's not, we'll have time now to jump into it whilst we do some practice. So if you go back to Portal, go to Practicals. Now with the Practicals, you can hit this Create Dummy Data. You can hit that button to open up the practical, and then down here, you can click Create Notebook. If you hit Create Notebook, it'll open up a new Google Colab notebook for you, and this is where we're going to code some of these examples up, right? This is a simple start example. I'll walk through this one. And show you guys this hands-on, and then I'll give you guys a chance to do it yourself. So. Let's take a few minutes now, stretch your legs, get started if you want. I'm just going to take a drink and then we'll get back into it. That's what we're going to do, all right? We'll do 3 minutes and then we'll get back to it.
Well done, that was great.
Sure, we'll be everywhere to get into the next group.
The combat might be like bombarding.
Yeah.
This camera.
Just graduate.
Is anyone's Discord mine doesn't work. You put a number What? 2 hours. How many things do you have? 4 hours. Magical man. It's a big chunky fish. So that's yeah. But I think you should be good. By randomly
It's an on-fire contract. Not a number. Failed.
I think you're right. It's just that I have to use AS type.
Just so the chat is not my last, so just don't put it or anything, okay? Just be careful with the chat.
Why is there new one? It's a difference between one type of section as well. You know what this is for? Is it still a robot? If you put 100
All right, let's get back into it. So before we do that, I just want to make one announcement, which is firstly raise your hands who's in Discord. Raise your hands if you're in Discord. Fantastic, cool. Our YouTube channel right now, there are so many people trying to join the live stream. We don't have enough subscribers, so they can't view the stream. So if you're in Discord, please do us a massive favor and go to the link which Ahmad just shared and subscribe to the YouTube channel, because there's a ton of people trying to join and apparently they're not able to. So it would really help out if you do that. That's a great excuse as well. So 1 minute to do that. I see you not doing it.
Yeah, well, like,
And these
All right, so let's get started with this practical then. Thanks for taking the time to, thanks for giving me the time to take a break. And yeah, I want to get the hands-on stuff now. So I'll run through this one, show you how I would approach it, and then give you guys a chance to implement it if you want. We're making pretty good time, so I don't think we need to be too rushed. And we'll do a few more of these practicals before we wrap up. So this practical is about creating dummy data. It says imagine a machine learning model. We're going to create some dummy data for it. We're not going to use a real data set right now, so just create some fake data. It's going to have 9 features, each between -1 and 1, and each of them is going to have a label, which is an integer between 0 and 3. So that's because it's a classification problem. The label is either going to be 0, 1, 2, or 3, because there's 4 different classes, 4 different labels for this one. So here, imported NumPy, so I can use NumPy as MP. And just wait for that to run. It's running. Now it's finished running. And in this cell, I'm going to create an array of 100 random integers and assign it to a variable called labels. So I'll do labels is equal to probably np.random.randint between 0 and 3. Is that how it works? I don't know. I don't expect you to remember it.
4 maybe, because if you put 3, that would be the higher bracket, so then you won't get 3 as the
Thank you. Okay, cool. So here you can see the documentation pops up. But let's pretend I didn't know that. I don't expect you guys to know that off the top. So here's what I would do. I would just go new tab. Okay, Python, Python, NumPy, random integers, array. Such that this is how you do it, and this is how I want you to approach all the practicals, right? I don't expect you to know them, I don't expect you to remember everything I say, I expect you to be able to figure it out for yourself, okay? So search that up, first thing that comes up, this is the function which I've used, and numpy.random.randint. Click in here, and here's the documentation, okay? This, if you take nothing away from these lectures and you want to get good at programming, this is the important part. It's to understand how to read this page and figure out what you need, because I don't remember any of the functions, and pretty much everything we can do, I'm going to have to look it up. Okay, and that's just the truth, that's what the job is. So here, how do I read this page? Critical to understand. Here's the title of what I'm looking at. I'm looking at something called random. It's inside this random module, which is inside of NumPy, which is a library for numerical stuff in Python. And you can see here, it's call sign, like this is how you call this thing, which is a function, it turns out, random. And you can see the different parameters which it takes in there. Below that, you've got a description of what it does. It says it returns random integers from low to high, and then below that you can see the details of the exact parameters that it takes in. Okay, so here's the parameters. It takes in low. This is the lowest integer to be drawn from the distribution. High, this is the highest number it can take, and then size. It says this is the output shape. So if the size is like this, 3 numbers inside a tuple, then that's how many samples you're going to get in your data. So this looks like what I want. I'm going to get random integers between my low and high. So go back to here. Go back to here. Randint, and it said, is it inclusive of the high?
No.
It's not inclusive of the high. Okay, cool. So yeah, thank you for the suggestion. We're going to have to do 0 to 4, and my size, I want that to be 100. Let's just see what comes out there. I got my labels, I print my labels. You can press this button to run the cell, or you can run the shortcut. I want to teach you guys all the shortcuts over these weeks. Hold shift, press enter to run the cell. There's my list of labels, right? That's what that's supposed to represent. So random data, just made it up, pulled out of the hat. Here's a different, each of these has a index between 0 and 4, and each of them represents what class this label is an example of. It might be I'm classifying between 4 different types of images, 4 different types of pets that someone might have in an image, and I want to classify what that is. So you turn that classification into an integer, which represents that class. We'll do more of that later. What I really want to get a handle on now is just the shape of the data. So now, I want to create an array that corresponds to your features, so that you have one set of features for each label. Well, let's say I've got features equals to, well, probably going to use NumPy again, np dot, what do I want here? I want just like a, it said between -1 and 1. Can I do whatever's in random? So in random, if I do the dot there, you can see what else comes up. Random, rand n, maybe. So that's going to give me the numbers from a random normal distribution. If I were just to do that and then print the features, I run that and it gives me just a single number, okay? So what I really want is like many of those numbers. So there's probably a size parameter for this. Again, I don't know where, sometimes the codes actually show up, sometimes they don't, so again, I'll just look it up. Right, NumPy, random, rand, n, search that up, here's the documentation. Scroll down, okay, it's got these parameters. It takes in however many parameters I want, I guess, and these are D0, D1, Dn. These are the dimensions of the returned array. It must be non-negative. So if I go back to here, my dimensions I want, what size do I want? Anybody remember? I've got 9 features, 100 examples. 100 by 9, exactly. Yeah, m by n, so 100 by 9. Question?
Did you want floating point integers though?
We'll get to that. So this is close enough, roughly. So run that. Now I've got this thing called features. If I print not my features, my features.shape, then you'll see it prints something different. It prints me 100 by 9. So really useful attribute to know about whenever you have a NumPy array, any of these vectors or matrices computed with NumPy, you can do the .shape attribute, and that will show you what the shape is. Really useful, really useful. Especially for debugging when things don't match up. You can't do a matrix multiplication because the sizes don't match, just print the .shape. Okay? So I'm going to keep blasting through this. I know it said something slightly different. It said between -1 and 1, and I think rand n, well obviously it's from a random normal distribution, but this is good enough, so we'll move on. There's probably another function just like that I could look up to get them within that fixed range. So now I've got my features on my label. Print the shape of my features label. That's exactly, my features variable. That's exactly what I did there. So that's fine. We've already done that. Print the shape of my labels. Print labels.shape. Run that. I get 100. And it says write a simple function to get the length of your data set, the number of rows in your features array. So I'll give you guys just 2 minutes to do that. That should be simple, and then somebody can help you write the answer. All right? Again, if that was really fast, don't worry. Like the point is, just try and look it up, and you'll be able to find out how it works. So search up, okay, Python, random number between 0 and 4. And even if you write it exactly like that, it will probably show you the right answer. Then it's just a case of getting familiar with reading the docs. It can feel really hard when you first start doing it. You're like, how do I read this thing? But that's the point. As you practice it, it becomes easy. Isn't that right?
Yeah, or you ask ChatGPT to explain it to you.
Exactly. That's another option. Other decks.
Yeah.
Good progress, guys.
I mean, I'm trying not to just like stare at what you're doing.
Well, it's hard to not do that. We're all sitting in a yes.
But
Oh yes, of course.
I think it's the code is the shapes the everything.
Yes, I'm struggling with this, and I'm just cheated by using like
Cool.
Is this too small?
These guys helping you out.
Yes, I've tried to do that.
I mean,
using like
all right, let's rock. There's 100 ways to do this. So the key thing, what you do is define a function. In Python, define a function with def, as you know. So I'll get data set length, like that. Always nice to give very verbose and obvious names, so you know what you're talking about. And then here I can just return, there's many ways to do this, either return the length of the features, or I could return something like features.shape. That's going to give me a tuple of 2 elements, 109, and so I could do just get the first one, like that, and then I could do get data set length, call that. I should probably not pass in the, I should probably not assume that the features are available. I should probably pass them in as a parameter up here. And then down here, pass in my features like that. Run that. That didn't work, did it? Because I need to get the 0th item there. Like that. So length of the data set is 100. Cool. Simple stuff. Nice. Let's do another example. This one is on data exploration. So back in the portal, create the notebook. This one uses some external files, so run the cell at the top. That installs everything that's necessary, and then run this cell just below. And it basically explains to you that you've got two NumPy arrays, I assume, called label data and features data, and then you can use this cell just to run this to load them in. So they've been stored in these files. We're going to load them in to features and labels variables. Find the shape of the features and labels variables. Features.shape. by 9 labels.shape. Run that, it's 100, that's cool. Do some exploratory data analysis, calculate the mean and the standard deviation of the features. For the rows where the label is 1, do the same for all features where the rows is labels are 2. Okay, this one's a bit more involved. How would I go about that? Any suggestions?
Have we changed notebook?
Yeah, we changed notebook. So back in portal, second practical. Any suggestions how would I go about this?
So you can probably deal with it with an if statement.
Okay, what do I want to if between?
You want if the label of the row is 1, then calculate mean and standard deviation, which I think you can do by NumPy.
Yeah, so if I'm going to use this if, this I kind of need to, so this is a vector right now, it's a long list of numbers. So if I run this, I think I'll get an error, it can't. Yeah, it says the truth value of any array with more than one element is ambiguous. So you're on the right lines, but you can't do that with the whole vector at once. You could do something like this.
Oh yeah.
Oh, sorry, I ran that by accident. For label and labels, then if the label is 1, then pass. But and as you'll see, the common trend as we go through things, what's more effective is to try and do it in like a vector implementation where you can do everything in parallel. So the way that I might do something like this is to say, okay, what do we want to do? So we want to index the labels where where the labels is equal to 1. How do we want to do that? So let's just look up again. Index where, something like that. So arg where, this says find the indices of the array elements that are non-zero grouped by an element. Is that what I want? No, that's going to get me the non-zero position. Get the index where a particular value is something. So you can do np.where. np.where where this thing is true. So how would I go about that? Do I want to do that? Mixing this between pandas, aren't we? Let's go with the for loop implementation first, and then we'll come back to that. So if the labels is equal to 1, then we'll save that index. So I'm going to say something like indices is some empty list, like this. And what I'm going to do is I'm going to go through the label in labels, and for each of those labels, if the label is 1, I will add to this list of indices. This will be a very trivial way to do it, and we'll do the vector implementation in a second. But we'll do indices.append the index. We need to get this index. So if I'm looping through a list, does anybody know how I can get which item of the list I'm in currently?
Can you repeat the question?
If I'm going through a list, how do I know which item of the list I'm in? How can I get the number of the position, the index I'm talking about right now? Tough one. This is a tough one. Question?
You think about labels and enumerate?
Absolutely. Yeah, exactly. So I could do something like this. Enumerate means that it's going to return two things. It's going to return the index and the label at the same time. And I can get the index like that. If I go through this and print the indices at the end, I'm overcomplicating things now, so we'll take a step back in a second. Run that. You can see here, here's the indices where the label is correct. Oh, sorry, where the label is 1. So these are the positions in my NumPy array where I have that label. Now if I try and index that labels with my indices, like this, let's see if that works. Then you can get the values out of the labels. But obviously we know the labels. What we want is the features. So if we do that, here is all features where those indices have that value number 1. Okay? And then what you can do is you can do np.standard deviation like that. So if I run that, we'll get a single value, which is this standard deviation of these features. Similarly, you could do mean. If I didn't know how to do that, again, just look it up, right? So NumPy, mean. Again, that's going to show you that right there. Same for standard deviation. So run that. You get the mean value. That's one way you can calculate it. This is really inefficient, so take a moment to do that, guys, and I'll do the vector implementation in a second.
We need to index features. So I'll be specific.
Yeah, would you run that?
Features is we need the corresponding
Okay, cool. So that's a trivial implementation. Any questions about that? No, we're good. Okay, cool. I'm going to do something a bit more fancy than here. This might be unfamiliar with you, depending on how familiar you are with Python. I want to do all of this in one line, basically. So I want to get the indices where the label is equal to true. And I've already got this list of features. That's why I want to find it in. So you can imagine that, well, you can see in here, I'm basically going through this, I'm going through this list of labels. I'm not just getting the label out, I'm also getting the index out. That's what enumerate does. And each time I do that, I'm basically asking if the label's 1, then add it to this list. So here, I'm going to do something more advanced. It's called list comprehension. So I can do something like this. I can do index for index, label in labels, if label equals to 1. So that's all of that in a single line. I've done that a little bit wrong, haven't I? Sorry? Sorry, what was that?
No, I said like you still need the enumeration.
Oh, yeah, thank you. So yeah, what this is going to do is basically do all of that in one line. So here's the kind of for loop bit, which you can see below here. And on the left-hand side, I'm basically saying, what do I want to get out of that? I want to get out the index. So for all of this, get the index out. Only do that if the label's 1. Let's run that again and see if the same indices come out. Looks good, looks the same. So that's a little bit more efficient way to do it. There is a better way to do that in NumPy. Just can't remember it right now, so I'll look that up in a second.
Are you using Macro?
Yes.
What's the keyboard shortcut to comment out multiple lines?
That's a great question. It's command /.
Thank you.
Yeah. If I do anything like that and you don't know what it is, please don't hesitate to stop me to do it. Okay, cool. So now it says use matplotlib to create a scatter plot. How would I do that? Let's look it up. Matplotlib scatter plot. Scatter plot. Okay, this one here. Take a look at this example. Again, more documentation. More documentation, guys. Important to understand how to use it. Again, all I did was search what I wanted to do in Python, open up the page. The first thing is, here's the name of what you're doing. Here's how you call this thing. So this is a function which creates a scatter plot of y versus x. And here's the parameters it takes. Sorry, that's super small, isn't it? And so you can see this is how you used it. You just call matplotlib.pyplot.scatter with x and y, and this should be fine. I'm going to import matplotlib.pyplot as plt, as I usually do, and I can just do plt.scatter my x and y. In this case, I've got many different x's, many different features, so I don't want to plot all of them. I'll just plot the first column. How do I, if I've got a matrix, how do I slice out the first column? Just the columns, not the row. How do I do it?
Square brackets,
You need to-
and then have a comma, then the. Actually, no, just square brackets in the row you want.
So square brackets, and this is going to give me the row I want if I just use one square bracket here. So if I were to do something like this, that would be the first row. But that's the first example. What I want is the first feature for all the examples.
Colon?
Sorry?
Colon?
Colon, comma, exactly. What does the colon do?
It selects all the rows.
Exactly, yeah. So that selects all the rows, and then I want to plot those against the labels. Something like that. Sorry, not as pyplot, as plt. See if that works. There it is. Okay.
Could you show again the previous implementation?
Yeah, for sure.
This one.
We could share these on Discord later if you guys want.
Cheers, please.
Yeah, you can send the notebooks complete.
Yeah, for sure. Cool. Everybody feel a bit more warmed up? You done some hands-on stuff now?
You talk through that first line all the time.
Absolutely, yeah. So this here, this is a list comprehension. It's one of the more advanced things you might see in Python, but it does exactly this in one line. And the simplest list comprehension you could have is something like this. Let's say I have a list which is 1, 2, 3, and I want to have a list of the squares of those values. So I could do basically what I want is a new list, and in that list, I'm going to, for now, let's just say value. I'll square it in a second. But now, then the question is, what am I going to iterate through? I'm going to go for value in my list. That's the simplest list comprehension you could have. This one does nothing to my list. It simply returns the same list. Okay? It simply, for each value in my list, it puts the value in this new list. Yeah. So what we want to do here is just square it, right? Double asterisk is power in Python. So something like that, and I should print it after, shouldn't I? Something just like that. So run that, and there's the squares. So that's a very simple list comprehension there, which should maybe make it clearer what's happening at the top. This one's a bit more fancy because it's got an if in. So essentially, this part is doing the mapping. This part is doing filtering. So you can map and filter with the list comprehension.
Could you show the last bit? I missed some of the list.
Sorry, this part?
Yeah, the one below with the very
Cool. Yeah, for sure.
Harry, is that more efficient than doing the for loop?
That's not more efficient. Yeah, it's not more efficient. It's just more compact. There probably is a really simple way to do it in NumPy. I don't want to get into it now and fiddle around with it.
We can ask ChatGPT.
But that's always the answer. Wait.
Are there cases where doing the compact format is more efficient than, or is it just
If you're storing something in memory which doesn't get wiped on each iteration, then it will be more efficient. Yeah. Because in that list comprehension, you don't create any new variables.
right?
Whereas you do in this one. Well, we don't really, but I guess we're storing these things. I'm not sure. It's not my fault. Okay, cool. So we've done the scatter, done all of that. I'll give you guys 3 minutes to have a play around with that. Make sure you can get comfortable with that. I know we're doing a lot. If you're not familiar with this stuff, it might be a bit of a rush. Grab me if you need, and then we'll move on. Can I scroll up a bit? To this part. I could break this down as well, just to be clear what's happening.
I'll try and have a look at these.
There's no reason. I think under the hood, doing the power notation, it calls NP not power. But I think under the hood, so a lot of the time you do things like, for example, you do on a number
I would write the whole thing.
Thank you. It's actually much simpler. I just messed it up. So just want to come back to this point. I made a really obvious mistake earlier, which was where we put it in an if statement. We said something like this. We said if labels is equal to 1, and that threw an error. Let me put that in a new cell. We ran that and it threw an error, and that threw me off because I was thinking, this is definitely how you get the indexes. The problem is that it's in an if statement there. So if you take it out and print that, then this is the vectorized way to do it. So this is basically a question. Where are the labels equal to 1? So if I print that again, then this gives you this Boolean array, okay? The problem was that this thing itself cannot be evaluated to true or false. So when we put it in this if statement, it threw me off and it gave this error. So what we have just there, that's the way to do it, okay?
That's the vectorized.
That's the vectorized implementation, yeah, exactly. Cool. Great. So any questions at this point?
Can you show the yes?
This one?
This one, thank you. No, sorry, the vectorized version.
That's right, yeah. So, quick question, just obvious Python one, difference between a single and a double equal sign?
Single is assignment, double is Boolean.
Yeah, exactly, yeah. Yeah, so single is assignment, double is comparison. Or equality. All right. Nice, let's keep moving through this. So that was the data, right? That was the data. That's the first part of the algorithm. Got to play around with it, should be more comfortable with what's going on now. The next thing is the model. The model is the thing that takes in the input and uses it to predict an output. Essentially, the model is this sum function in between these two things. You got some data, you got some features, you got some labels. There is some function that maps between those two things. We call that the model. So this is like the first key piece of jargon, which you will not hear the end of, is machine learning model. Right? You're going to hear that everywhere. ChatGPT is well, maybe not itself, but GPT-3 is a machine learning model, for example. But all it is really is that function that performs that mapping. That's the important thing. Whatever your input and output, then your model is the function which maps between them. So it might take a set of text and predict the next word. It might take in the joint positions and accelerations of a robot, use it to predict the next move, and so on, right? So the model it can be implemented anything you want, right? Any kind of function, you can write it yourself. It could be very simple, it could be a straight line equation, it could be something very complicated like a transformer, and we will get onto building more and more complicated versions of those models. So to just show a very simple example, because I won't get into the practical now, which kind of covers that. This one's a bit long, and I think we might run out of time. So I'll just show you a very simple implementation. You might have something like, let's say I've got a new cell, and I just say I define my model. It might take in some x features and return 2x plus 3. Okay, straight line equation like that. Then I could call my model on some data. Call it on 4. It's going to give me some output. So that's the simplest possible version of a model which you could have. And this straight line equation, this linear transformation, is actually something we'll look at a lot next week and cover in detail, because it's one of the key components of these deep learning systems. So that's really the essential thing you need to know there. The model performs that equation. It could perform something more complicated, like whatever, NP dot, so on. Could have a very complicated function there. And when you have these deep neural networks that we'll look at very shortly over the next 2 days, that is what's implemented on this line, essentially, or maybe over a lot of lines, defining how do I take in the input, how do I transform it, not just with a simple straight line equation, but with something more complex that builds and builds and builds on each other over many transformations. That's what then returns the output. So the model performs that mapping, and it's just a mathematical function. That's it, simple. So to continue from there, the third thing is what we call the criterion. So the criterion, the key point to remember here is that the criterion is simply a measure of how bad the model is right now. Because what we're going to do is, as we said, machine learning, and the point of that is that you are going to learn this function for yourself. You start off with a random function, something very bad. It's going to be totally random. And what you want to do is measure how bad is it when you first initialize it, and then change it, and then measure how bad it is again, and hopefully move in the right direction over time, right? So you need something that can tell you, given the model and its current predictions, comparing this with label, how bad is it right now? And that's what the criterion does. So you might also call it the loss or the error. And the most common one that you'll encounter is the mean squared error. So the mean squared error is the most common loss function used for regression problems. Regression being where you're predicting a continuous output, it can take any number. The other case being classification, where you're predicting a discrete value. So in the example I said, where we're predicting between 4 different types of images, that's a classification example. Whereas predicting the house price, that's a regression example, because the examples can take any value. So the mean squared error is the most common loss function used for the regression problem. It looks something like this. It looks complicated, not really when you break it down into components. It's simply the average difference between the predictions, y hat, and the labels, y squared. Okay, that's how you measure the difference. It's squared because otherwise positive and negative differences might cancel each other out, and it's average so you get an idea of, in general, like what's the error for all of my different examples. This is one of the different criterions, the measures of how bad the loss is, how bad the model is, which you're going to use to make sure you can get a useful model by the end of things. So really important to understand this. This is we'll build on this until things get very complicated. Questions about mean squared error, anything like that? Simple. It looks something like this. So if you make a prediction, which is over here, and the true label is over here, then this is how bad your model is going to be. The mean squared error loss is going to look like this. Grows quadratically as you get further away. Should make sense based on that equation above. If this is bigger, then I square it, the loss gets bigger, either direction.
Why is it called loss?
It's a good question.
I never understood it.
Yeah. Loss of performance, maybe, something like that.
Fair enough.
Gold star if you look it up. But yeah, loss, error, cost, another way to call it. This is one of the most common loss functions that you see. The other one is for classification, which is the cross-entropy loss. We'll probably go over this in more detail later. This one's a little bit more involved, but it looks like this. More helpful is the diagram, really. Actually, maybe if I can't show both at once, so I'll just show you the diagram. Essentially, when you're doing a classification, you want to predict a probability of each different class. And for the correct class, you want the probability to be 1. You want it to be, like, I'm fully confident that this is the correct label. But for the correct class, as the prediction is less and less likely, as your model predicts like low probability, you want to say this model is really bad. So that's what the cross entropy does here. You see I've got this curve down here. It goes down to 0 when the predicted probability for the correct class is 1. So when the model correctly predicts the correct class exactly, perfect, there's no loss. When it predicts 0 for the correct class, that's very bad. It should be infinitely bad. And so this is a curve which tends up to infinity as it approaches 0 and approaches down to and reaches 0 when the correct class is predicted as in 1. 1 probability, total confidence. And so that's this equation up here. It's the average negative log likelihood of the probability predicted for the true class label. That's the important part, for the true class label. Given the right class, this should have a high probability, and then this negative log here is this curve. Looks nice, like that. Cool, I think there's a practical for this. So let's do that. We'll take 10 minutes, and you guys, I'm going to do this. I'm going to let you guys do this one on your own, and then maybe you can help me implement it, and then we'll come back to the final component. All right?
Just getting going. Get everyone up to control. But then there'll also be people in here they could have covered employment with their dedication. You're staying up to the whole I don't know.
We've found we have twice as many full values.
Someone just pointed out that there's twice as many labels as there are features. It's a bug, so just cut them off. Slice them off.
Could you explain that, what you just said? What?
Yeah. I'll do a demo. So in this loss curves practical, if I just create a notebook and run the first few cells, then you will see if you print the shape of okay, so if you guys print the shape of these two things, you'll see they're not the same as mine. Mine are different because I'm on an updated version. But you'll see that yours are too long. So what you want to do is something like this. Whichever one is longer, you want to index out the first 100. not just the 100th one, but you want to index all the way up to the 100th one. So colon 100, and if I print that dot shape, then you'll see that that truncates off the last half. So you guys want to do something like that.
Thank you.
All good?
Do you mind going back to that cell?
This one?
Yeah, thank you.
Sorry.
Why do we need the colon in front of the 100?
What's that?
Why do we need the colon in front of the 100?
Because that says, so index all the way up to 1. So if you want to cut out, say, between the 50 to 100 example, you do something like that. That gets you a range of slices of the data.
You just do like square brackets 100 without the colon.
If you do square brackets 100, it will get you the 100th example.
Oh, I see.
Yeah. So either you're indexing or you're slicing. Right. So that's me slicing, that's me indexing.
So the colon means up to 100.
Yeah, exactly. Or it could mean, for example, from 20 to 100, or from 20 to 100. Okay, so I'll run through this. I'll run through this example. I know yours looks slightly different to mine. Mine's a slightly easier version because it's been updated recently. So I'll talk you through this. In my case, I've got these two different things, which are 200 by 4. That's their shape. It's 200 different time steps, and a batch of 4 examples and their corresponding predictions at each time step. So we're not looking at the feature matrix here. We're looking at something slightly different. So again, 200 different time steps and predictions and inputs at each of those time steps. So we want to, predictions and labels at each of those time steps, which we want to compare. Okay? So we've got the true values and the predicted values, and it says they're arranged in batches. So I've got batches of 4 examples at any given time step. And what I want to do is define a function to compute the mean squared error between these two things. So I've got the true values and the predicted values. What I want to do is I want to calculate that mean squared error. I'll see if I can do it in one line. If it's too complicated, we'll break it up. So yeah, I'll return something like, in fact, if you look back at the equation we had, you can see the exact equation there, right? So translating that to code, that's another key skill. In a lot of machine learning and deep learning papers, you'll see obviously all kind of equations, and being able to put them into code, that's another key skill. So this one, right, I've got an average here. I can use numpy to calculate the average. I can just do numpy.mean, like that. Again, if I didn't know that, I just search numpy mean. There's the documentation. I want to take the mean of, what is it? It's the difference between the predicted values, y hat, and the true values y squared. So I just take the true values minus the predicted values, and all of that I want to be squared to the power of 2, like that. So that should give me a scalar value for each of these, which is the mean squared error for each batch. Now what I'll do, just to keep it simple, is again we'll just do a for loop. So I'll do for index in range length of the true values. So basically just give me an index for each position in time, 0, 1, 2, 3, all the way to 200. For each of those, I want to get out the true label at that position, at the index, and I want to get out the predicted values at that index, and those are the things which I want to pass into this function. You could probably actually pass in both of those matrices and do the whole thing vectorized, but just imagine we're getting each batch at a different time step, going through a loop, make an update, calculate the mean squared error. Sorry, question?
So each array has 400 items, right? So this function npmin and the subtraction would be applied to every pair of items.
Yeah, so that's the more complicated case, which I'm not going to do here because I've just got a for loop. So if I just go through each of these 200 rows in my case, I'm just going to take a row at a time. So I've got these two matrices. I'm just going to go, okay, firstly, take the first row, calculate the mean squared error. Nextly, take the second row,
But there are
calculate the mean squared
4
error.
columns in the first row, right?
Yeah, and in this case, they represent 4 different examples. The labels for those examples and the predictions for those examples. And so, yes, actually, you're exactly right. That's what I'm taking the mean of over here. So essentially, I've got 2 vectors. I've got a vector of predictions and a vector of, vector of predictions and a vector of labels. I want to take them away from each other, and that'll give me a vector of the differences. That'll give me this thing as a vector. The difference between the predictions and the labels. And then if I square that, it's going to square them element-wise. So then I have a vector of the squared differences. And then I take the mean of that by doing this. So np.mean of the vector of the squared differences, which is that. Make sense?
Yes, thank you.
Sweet, good stuff. Someone corrected my spelling over
So
there.
it's predictor,
Predicted, there you go, predicted.
and I think you're going to need to say true values, not labels.
Thank you so much. There we go. True values and predicted values. So each of these is a 4 vector. Okay? I've got a vector of I've got 4 different examples in each of those. And I'll pass those into my batch mean squared error function. So I'll call that on my predictions and my labels.
So that entire loop is just you're subsetting it, or what does that second part do? Why are you writing the for?
So you can imagine what we'll look at later is that you don't. What we'll look at later is that you have a model that's initially very bad. You see how bad it is by doing this, and then you update it. And then you see how bad it is for the next example, and you update it time step after time step. So that's kind of what this is trying to emulate. You can imagine that, okay, in this for loop you've got 2 things. You've got compute the loss, and then down here you've got like update the parameters, something like that. Which is why I put it in the for loop, because there's no case where you're really going to have, okay, here's my predictions and my labels over the whole time, and I've already done all that, but I haven't computed the loss yet. It's the point of computing the loss is so that you can change. Cool. So if I run this now, we'll see if it works, see if I made a mistake anywhere. There's the loss over time, right? This kind of thing we'll actually see a lot as we go forward. When we have some machine learning model, we make a set of predictions and we want to, and we basically want to track how it's doing over time. We'll see these losses printed. It's very hard to see, is it doing well though, right? The question is, like, what should it look like, firstly? It should look something like this. This is a good loss curve. So having computed the loss, over time, what does it look like? You want your model to get better and better. That is your loss to go down over time. And so this is a good looking loss curve. That's what you want it to look like. That's converging. It's converging on more accurate parameters. And a bad one would look like something that either stays flat or gets worse. And we'll look at more complicated examples in a second. So now that I've got that loss, I probably want to have that in a list, right? So let's say I've got a list of losses, like that. And at the end of this, I just append my loss to it. And then my losses will be a list of these different values. If I run that, I'll get that list. And now I can just do, that's the canonical import. I'll just do plt dot, what is it, plt dot line. Plot. So if I do plt dot plot, my losses, see what happens. Looks like that. That's not good. So that's a typical thing you might kind of see, but what you want to see is it curving down. So if you see something like that, you can see it's not converging. What we're looking for is that. That's what we're looking for. In the very least case, right? That can still be bad, but that's what we want generally, is loss goes down over time. Awesome. I'll give you guys 5 minutes to do that, and then we'll cover one more thing, and we'll wrap up.
Can you show the calculation?
Yeah, for sure.
No, the one.
So you don't get a single value for mean squared error then?
You do, but so you can see for each of these pairs of predictions and labels at a different time step, we've got a single number, which is this loss. And at the end of the training, the last value in that list, that's the final single value. That's like a measure of how bad the model is at the end of the training. So that's probably what you're thinking about. Make sense so far? Yeah. He probably hasn't truncated
Another web.
It's just a bug. Cool. All right. Let's keep moving. We're almost there. I'm gonna jump into the next thing, which is beyond the loss curve. The question is, how does it get better? How does it actually get better? Well, I've said it should go down over time, but what's happening over time to make it better? Well, we saw originally that these models are simply controlled by parameters. So you change the parameters, and the input-output function changes. And the optimization is the process of improving those parameters. So this is the final component, optimization. So optimizer is the algorithm used to update the model parameters. And this is what the learning in machine learning is. It's simply like improving those parameters. And as you do that, you say that your model is learning to represent that input-output relationship more accurately. So the most important algorithm to be aware of is gradient descent. I'm not going to get into all the details here, but it generally works like this. You get an example, you make a prediction by passing that example through your model, you compare the prediction with your targets to compute the loss, and then you update the function parameters in a way that moves that loss, that decreases that loss, essentially. And then you do that step by step. So okay, I've got a current model, I made a prediction, they were this bad, and I can see on my, I can see looking at my loss function that if the prediction were higher, then the loss would be lower. So I should move the parameters in a way which makes the loss lower. Just do that small steps at a time, step by step, until it gets a lot better. You can imagine it doing something like this, right? So this is a 3D plot where the surface on the bottom, where the grid on the bottom represents the different parameters of the model. As you change those parameters, the loss, which is the vertical axis, can change as well. So for different parameterizations, given the same data, the loss will be different. Because the parameterization controls, does the model represent the function I want it to or not? And so as you change the parameters, the loss decreases. So this is, it depends how you change them, of course, but in this case, what I'm doing is this gradient descent process. Why it's called gradient descent is because I'm descending down the loss surface by following the gradient downhill, okay? So this surface here represents how bad the model is. I want to go down that surface. So at any given point, look at which direction is downhill, move in that direction. That direction downhill is the opposite of what we call the gradient. So the gradient is, at any given point on the surface, there's an arrow which is pointing in the direction which is most uphill. You want to move in the opposite of that direction. And so mathematically, you guys can read all of this in later tonight or before tomorrow. Mathematically, you would say it does something like this. This is the gradient descent update step. What this says here, I should have done this one in color because it would have been easier to understand, but the left arrow says basically set equal to. So I've got my current parameters, set them equal to what they were previously in the opposite direction of the gradient, the downhill slope. And then just take a small step, just scale that step size down by alpha. Again, we don't need to understand too much of this to go into the high level that we'll look at. There's a lot more that we can get into, but we're not going to get into this session. But a lot of this will be taken care of behind the scenes. The most important thing to understand is this graph, right? This is really how most of the algorithms that we talk about are optimized. You've got some measure of how bad the model is. That forms this surface above all the different parameters. And as you update the parameters, by moving them in the direction which is downhill, the model gets better, okay? Again, this is covered in the machine learning essentials pathway, so if you're not familiar with that yet, please just check that out in the Aicore portal. You'll be able to find it here on your account. But this is just the main overview. So moving on from that, that's the process of how we'll optimize these models. We're coming up to 5 minutes from the end now, so I think that I'll try and blast through this stuff and we might run 5 minutes over. All right? Cool. So one thing is we're going to see a lot of vectors, and when you look at these things that I'm going to draw, it can be very unobvious how to think about them. But really, you can just think of them as an extension of 3D space, right? So you know what 1D would look like, you can imagine that, it's just a straight line. You know what 2D would look like, it's a grid. You know what 3D would look like because you live in it. And anything higher than that is just, think about it as the same thing, just with more axes. I know you can't visualize that, but just try and think about it as the same thing. It extends like this, all the way up to ND. So very shortly, we'll be talking about 128 dimensional vectors. And it's no more complicated than a 2D vector, right? So just think about it in the same way. I think there's a quote here. Yeah, to visualize 13-dimensional space, think about 3-dimensional space and just say 13 loudly. That's how to do it. So just think about it like that. We're also going to see another term called hyperparameters. So there are a bunch of configuration that you can set for all the machine learning models that we're using the algorithms that we'll be talking about, and those things need to be set before you start doing this optimization process. The optimization updates the model parameters, but the hyperparameters are things you need to set before or are hard to train. So just a difference there. The parameters get updated by gradient descent. The hyperparameters are like configuration. Basically things like, okay, what's the step size of the gradient descent? how big's the batch of examples, how long am I going to train the model for, that sort of thing. More detail here, I'll leave you to look into that, and we'll talk about the test sets later. Actually, yeah, we'll talk about that as a final thing, and then we'll wrap up. Okay. So when we have our, where are we? Where have we gone? Okay, yeah. So with our data, what we typically do is split it into three pieces. One piece is the training set. This is the one that you use to make the predictions and compare them with the true values, and then update the parameters in a way that the model gets better. Once you've done that, you want to have an idea of, okay, how's this going to perform on new examples, stuff that I haven't seen yet. And that's what you use the validation set for. You don't want to train on the validation set, because otherwise you're going to do well on it, because you've seen it already. So you want to keep that set aside. But there are other things, other decisions about the model which you do want to make, and you need to have some you need to have already learnt the parameters to compare them to. So for example, you might train 10 different models with 10 different batch sizes, and you want to know, well, what's the best batch size? You can't make a decision about that data based on how you're going to, based on the data which you're going to report the performance of the model on, because otherwise you'd be choosing the best batch size by already knowing which data set you're going to look at. So what you need to do instead is have, instead of just having a test set, which is what you report your performance on, you need to have a validation set to choose your hyperparameters. So the training set, you use to learn your model parameters. The validation set, you use to compare different models. Make decisions about the different models, but not to report the final performance. And the test set is used for one thing and one thing only, which is reporting the final performance. Okay? And as a result of that, question.
So what happens when I test my data on the test set, and then it comes up back, all the metrics are terrible, then surely if I change my model, then I'm using data from the test set to evaluate my model. So what do you do when the test turns out to be bad?
Well, the test is a measure of, the test is like how you report what you expect this model to do, right? You don't make any decisions about it, but you use that as like, is this even safe kind of thing, right? If I'm creating a self-driving car, it needs to be above like a really serious threshold to be safe. And that test set, that's what's used to compute that number, which you report as, you know, this is how well we expect it to do. We haven't made any decisions about the model on this data, so we know it's not fit just particularly well to do well on this test set. So, so you would have that metric and you'd say, right, this one's clearly not safe, we shouldn't use this one.
Okay.
Does that make sense?
Yes.
We're rushing through things, I know it's fast, we'll dive into it later if you want.
So is test data used to measure absolute performance of your model, basically?
Yeah, it's used to report it after you've done the training. So if you're putting something into the wild, like that's the value you can expect.
And then would validation just be to check if your model's like generalizing to the data?
Validation is to compare different models. So you can imagine that, let's say I have 5 different models, 5 different mathematical functions. They're all initialized randomly. But when I train them on the training set, then they'll have good parameters. The question is, which of these is best? That's what I would use to compare, that's what I would use the validation set for. How well do each of them perform on the validation set? And then, whichever is best there, I can make a decision to pick that model. So I'm making a decision about which model I use based on the validation set. So I shouldn't report the performance on the validation set because I've kind of cherry-picked it already. I've already said, okay, I know this model is going to do well on that. So that's what I use the final test set for. Final test set is just to report performance. Keep it simple. Training set, find the parameters. The validation set, choose between models, aka choose the hyperparameters. And the test set, report performance. Question?
How do you make sure that the data in these free trainings, like in these free sets, is not autocorrelated?
Sorry, out of what?
It's not autocorrelated, like it's independent.
Yeah,
Like how do
you should have a big enough data set. Is basically one thing. And if you want, compare the distributions between what appears in each data set. Great question.
So the books the validation set and the test set on the same
They're unclean, did you say?
Models have never seen this data.
Yeah, unseen data. Yeah.
Just
Yeah.
data validated.
Yeah, exactly. So the model is not, the parameters of the model are not chosen based on the validation of the test set, but the hyperparameters are chosen on the validation set. I'd love to go into more detail with that, guys, but I know we're going to run out of time now. So I wanted to mention just one thing, and then we'll get to it.
That's it, but I think you can't do it, but I think for space it'll mark it.
So guys, let me go through this, and I'll let you go. So we've already done that. No time for intermission today. I want to give away some prizes this week. So I want to make this as fun and engaging, and I want to keep all of you here for as much as possible. So I've got a bunch of stuff to give away, not just this stuff, but some cool stuff. And I really want you to be a part of it, and I don't need it anyway. So if you want to be part of winning some of this kit, then this is what you should do. You should post about building the future and big yourself up online, because you're really doing it, and I think this is probably the first time it's happening anywhere. You should tag Aicore and myself, and at the end of the week, we'll pick a winner from our favorites. So the more times you enter with good stuff, the more likely you are to get picked, right?
You should also be on the Discord server.
You also have to be on the Discord server to win. And at the end of the week, I'll give one of you something awesome, all right? With that, it's my pleasure to have you here for the first session. I'm really excited to get started. Let's do it.
Thank you.
Oh man, are we going for drinks?
Yeah, we're going for drinks.
We're going for drinks. Oh, no, it's a. Thank you. This is what I'm going to do. I'm just going to do it right now. You see me do it? So I'm going to do two things.
Okay, see you.
One is my engineering team.
Can I ask just one thing? So this online video will be kept for, you know, as long as, or you just after call?